Good morning, this is Jennifer Martinez. In this video, we're going to calculate limits at infinity by hand using algebra. In the last section, we looked at how to calculate limits at infinity by using technology, our calculator, from a graph or a table. This is an example, actually, from the last section. And you can see the answer to both of these is 0, which I'll explain in a minute. But we're going to use this fact to learn how to calculate harder limits by hand. Okay, so it says here the graph of f of x equals 1 over x in a large window shows 1 over x approaching 0 as x grows large in magnitude, either in the positive or negative direction. So if you look at this figure, as x goes large here, goes to 0. That's as x goes to infinity. And as x goes to negative infinity, it's also going to 0. This is what we would expect, since dividing 1 by a larger and larger numbers yields answers which are closer and closer to 0. So it suggests this, which makes sense because the function has a horizontal asymptote at y equals 0. You can also see this by making a table. Let's look at f of x equals 1 over x. And if we plug in a 10, we get a 1/10, which is 0.1, 100th, 0.01, 1,000th, right? 0.001. So the larger and larger x gets, the smaller and smaller the f of x gets, which suggests that that would be true. We can do it for negative as well. Same function. This would be negative 1/10. It would not change anything. Even as these values, even though these values are negative, they're going to 0. So we have it. Okay, so let's use this to calculate this limit from this section. So to evaluate this limit, I'm going to multiply numerator and denominator by 1 over y. So if I did this, what do we get? The numerator would be 3 over y plus the y's would cancel when I distribute. I'm just going to distribute this, plus 4. And then this would be distributing this, 1 plus 2 over y. So here, when I take the limit as y goes to infinity here, you cannot calculate anything by hand. Yes, you could graph it on a calculator, and yes, you could make a table. You can always do that. But if you want to do it algebraically, you can see here that if I just use this idea of multiplying top and bottom by what we're going to do is the largest power of y, and use our property of limits, because now we know this is the limit of the top over the limit of the bottom, we know from above that this is 0. So it looks like this would be 0 plus 4, so the answer would be 4, and this would be 1 plus 0. I could even write that. So the answer is 4 over 1, not 0. If you actually found the horizontal intercept to this, you would realize that it's at y equals 4. You could try graphing it and see. So let's look at another example. Notice in this second example that the numerator is a higher power than the denominator. In the example that we had above, the example 5, the numerator and the denominator were the same power. So what was kind of happening as the numerator was behaving like y, and the denominator was behaving like y, and so really it was like saying 4y over y, which is kind of what we got here, just the numerators, and it ended up being 4. On this example, the numerator is a higher power than the denominator. So my guess, I think it's obvious that x would go to infinity. And you can see this if you graph this on the calculator, that there is no horizontal asymptote when the numerator is higher than the denominator. In fact, we saw in pre-calculus it was in a diagonal asymptote. But let's go ahead and do this. To do this one, what I'm going to do is I'm going to multiply top and bottom by the 1 over x and just see what happens. This would be an x plus 2 over just 2. Oops. And then the denominator would be a 1 plus 1 over x. And you can see here, as x goes to infinity, this is 0, but we still have that infinity up there. The bottom is going to 1 plus 0, so the bottom is going to 1, but the top is going to infinity. So this goes to infinity over 1, which is just infinity. And you have to be careful as x goes to a negative infinity. This would be negative infinity. If this was a squared there, then it would still go to positive infinity. So we'll see some examples of those. If you have higher powers, it's still going to be the same thing. Well, let's look at this. Now, on this one, I don't want to do 1 over x because that's not going to give us anything, because then or 1 over z. I always like to do the highest power in the denominator. I personally don't like the denominator to end up being 0 there. So on number 27 here, I'm going to take this and multiply top and bottom by 1 over z cubed. And what do you think the answer is going to be? By the way, the higher power is now in the denominator. So my guess is going to look like a 1 over z, which is going to go to 0. Notice how this one looks like an x, so it went to infinity. This one again was on the same level, so that's why it was 4. So let's go ahead and try it. So I'm going to multiply top and bottom by 1 over z cubed. And what am I going to get? I get 5 over z plus 2 over z squared plus 1 over z cubed. Here we just get a 2, 1 over z, and a 9 over z cubed. If I go ahead and look at both the numerator and the denominator, the numerator just goes to 0, and the denominator goes to 2, which is what our instincts should have been. Number 28. Hopefully you can start seeing the pattern now. You can actually do these without any algebra at all by visualization. Notice how the numerator, the highest power is x squared, and the denominator, the highest power is x squared. So this is going to signify just a 7x squared over 3x squared. So probably it's going to be 7 thirds. So the highest power of each is what it's going to dominate. On 27, the highest power in the numerator was 5z squared. The highest power in the denominator was 5z cubed. And if you just looked at those, you would get a 1 over z, which is 0. And again, in this example, the highest exponent was x squared and the highest exponent was x. So if you look at just that, it's x squared over x, which is just x, which went to infinity. Interesting, huh? But let's go ahead and show this. The highest exponent in the denominator is x squared, so I'm going to multiply top and bottom by x squared, 1 over x squared. And we're going to get a 1 over x, a 7, a negative 11 over x squared, a 3, and a negative 2 over x. And you notice that that would be 7, because these two would be 0, and a 3. It works. So what about these? What do you think? This is definitely going to go to 0. This is going to be a constant, so it's probably going to be 4/5. Let's check that out because these are the same level. Now this one you might want to go ahead and do, or if it said show work, let's show our work for this. I'm going to multiply top and bottom by e to the negative t this time, which is the same as 1 over e to the t, since this is the highest exponent in the denominator. So we end up with these canceling, just giving it a 4. This would be a negative 2t, since I would add those exponents. This would cancel, giving me just a 5, and then I'm just going to say 1 minus t there. And you can see this is like saying 3 over e to the 2t. And then this one, I'm just going to change that to e to the 1 over 2t. As you can clearly see that this is going to go to 0. And this one is going to go to 0. So the answer is 4/5, just like we thought. Last one, maybe the second to last one, number 30. So what are we going to do here? When these are different bases, I might want to rewrite these and get them in the same base. So I'm going to take the limit as x goes to infinity. And what I'm going to do is separate these. 2 to the x and a 2, 3 to the x, 3 to the negative 1. Okay, I can deal with that because we could just put that in the numerator. So that would be like 1/3, wouldn't it? Or a 9 up there. Oh, I'm not, sorry, not a 9. So you multiply the top one by 3 as 6. Now that these are the same exponent, I can rewrite this as 6 2/3 to the x. And what happens there? If you have something that's a fraction less than 1 going to infinity, this is going to end up being 0. Why? Because this is an exponential function, right? Some a to the x. It doesn't matter what the number is. You can call it ba to the x if you'd rather. And we know that when the a is less than 1, it's decaying. It's a decay function. Yes, for a larger than 1, you would have something like this. It would be a growth. So you really, it depends on that base there. So if you had this example, we would have just switched those. This would have been infinity. So getting this all on one screen, you can see the whole explanation there. The first one was 0, and this example was infinity. So now we have seen 3 ways of finding limits. We have by hand using algebra. That's what we did here. But in the last sections, we also saw we could graph or make a table. Those are the 3 methods. If I don't specify, any one of those 3 methods would do. So any one of these could be done by graphing on your calculator or by making a table. This is just the algebraic approach, if you would rather. I hope that helps.